The CPPC. Welcome to today's CPPC seminar. It's my great pleasure to introduce Ameek Malhotra. Ameek received his PhD from UNSW a couple of years ago, and now he is a postdoc at Swansea University. At the moment, he's visiting us as a Gordon Godfrey visitor, and he'll be here until December. So today he'll be talking about gravitational waves and Bayesian model selection. Please.
Okay. Thank you, Jan, for the introduction. It's a great pleasure to be here at UNSW. There's some audio issue. I think that's just the wind. That was the wind. Okay. Anyway, it's a great pleasure to be here in person at UNSW and present my work on gravitational waves and Bayesian model selection in early universe cosmology. These topics, this time, I will treat them separately. So gravitational waves as a separate topic and Bayesian model selection as a separate topic. But of course, there are always links, and Bayesian model selection is also important for gravitational waves as well. So this presentation will be based on work that I've done with people at Swansea, so Marisol, Giamassimo, and Yvonne, but also people at UNSW, Nathan and Jan. So the first part, I will discuss the recent announcement by PTA collaborations about evidence for gravitational waves. And I will discuss the role of gravitational wave anisotropies as a tool to try to identify if the signal is of astrophysical, so supermassive black hole binaries, or some early universe origin. So then I will present some results related to current constraints and forecasts on these anisotropies. So in the second part, I'll discuss the issue of Bayesian model selection for cosmology using a new technique called Bayesian optimization and how it can be used to calculate the evidence, which is an important quantity for this model selection process, in situations where traditional methods might not be the most suited. So let's start with the first part, gravitational waves and pulsar timing arrays for cosmology. And this is work based on work I did with the Swansea cosmology group. So firstly, you all know that gravitational waves can be detected across a wide frequency range, so from ground-based experiments, which are at Hertz frequencies, to even up to CMB scales, which have time periods of billions of years. And there's a wide variety of sources. On the astrophysical side, you have mergers of compact objects. And on the cosmological or early universe side, you have various processes that might be operating in the early universe that produce such gravitational waves. Now today, I'll be focusing on pulsar timing arrays, which operate in the nanohertz frequency range, so with periods of years or so. And in this range, the main sources come from mergers of supermassive black hole binaries, so black holes which have masses of the order of millions or even millions of solar masses or even more. And the other possibility is early universe processes, which could include inflation, phase transition, cosmic strings, and so on. So the idea behind gravitational wave detection with PTAs is the fact that pulsars or millisecond pulsars, which are used for these detections, are like cosmic clocks because they emit pulses at extremely regular intervals. And this fact allows us to detect gravitational waves through the effect of these gravitational waves on the distance between the Earth pulsar baseline. So if there's a gravitational wave passing through, it will change the length between the Earth and the pulsar and lead to deviations in the expected time of arrival. Is there a question? No. Okay. And this will lead to deviations in the expected time of arrival in a manner which is correlated across different pulsars. And this correlation for an isotropic background, so a background which looks the same in all directions, is described by the Hellingsdown curve, shown here in blue. And the Hellingsdown curve essentially tells you what is the correlation as the function of the angle between the line of sight to the different pulsars. So this correlation is nearly quadrupolar, which reflects the quadrupolar nature of gravitational waves in general relativity. So it's maximum when the line of sight of the pulsars is aligned. It goes down close to below zero, the minimum value close to 90-degree separation, and then it comes back up at 180-degree separations. So recently, several pulsar timing arrays have announced strong evidence for such a stochastic gravitational wave background. These include the American, the European, the Australian, Indian, as well as the Chinese collaborations. So the significance of this evidence ranges from 2 to 4 sigma, depending on the different collaborations, which have different data sets and so on. And so the evidence for the correlations, for the HT correlations, ranges from 2 to 4 sigma. And what they already have is modeling the gravitational wave spectrum as a power law in the intensity, for instance, is to get constraints on the amplitude A and the spectral index, denoted as gamma, of the gravitational wave background. But the question we want to try to address is, what is the origin of this signal? The most likely contender, and the one we expect, is the supermassive black hole binaries, because this is expected to have an amplitude which is roughly in the ballpark of what has been detected, and as well as the spectral shape. And this was calculated quite a while ago to have these properties. Although there are minor hints of, perhaps one could say, tension with the predictions of simplest models, but it's too early to say anything, I would say. On the other hand, a lot more speculative, but perhaps more exciting for people listening here, is that the signal comes from some exotic process in the early universe. So some non-standard inflationary scenario, large density perturbations associated to primordial black hole formations, some phase transitions, and many other possibilities that people have studied recently. I will lump all of these different processes into one single category, and I'll refer to them as cosmological or early universe sources, because what I want to address is the question of whether we can distinguish whether if the background is coming from astrophysical or early universe sources. So how do we plan to do that? The idea is that we want to look at additional gravitational wave background properties, so beyond just the amplitude and spectral shape, try to figure out the origin. And what we want to specifically look at are gravitational wave anisotropies and see what the two different scenarios predict. If the predictions are sufficiently different, we can then try to, given a future detection of anisotropies or non-detection, try to figure out the origin. At the moment, the data is completely consistent with an isotropic background, but this might change in the future. Yeah. So just as a note on formalism, to describe anisotropies, we will use the spherical harmonic basis. So the anisotropies, which represent the distribution of energy density in the sky, and we represent it in the spherical harmonic basis. And the key quantity that I'll refer to is the angular power spectrum. The angular power spectrum, the CL, which is the quadratic expectation value of the spherical harmonic coefficients, ALM. So the multiple index L tells you the angular scale of variation of this energy density or intensity. So small l corresponds to variations across large angular scales, and large L corresponds to variations on very small angular scales. Now, for the first supermassive black hole scenario, there are different estimates in the literature, but more or less they all agree that these anisotropies are expected to be large. In terms of the CL, this predictions lie between 10 to the minus 1 to 10 to the minus 2 with respect to the monopole. And the reason behind this is that supermassive black holes are, these sources are discrete in nature, and they also trace the large-scale structure, which itself is inhomogeneously distributed. As a result, these anisotropies are quite large compared to what we expect for cosmological backgrounds. Now, for cosmological backgrounds, the anisotropies are produced either at the time the gravitational wave background itself is produced. So these would then inherit the properties of the production mechanism. So if there are some initial inhomogeneities in the production mechanism, these would be imprinted on the anisotropies. But then also, because gravitational waves propagate in a background which is itself is inhomogeneous, so propagate through large-scale density perturbations, they also pick up some anisotropies along the way. So this is very similar to what happens for CMB as well. But on the other hand, because we have measured CMB anisotropies already, this gives us an indication of what the early universe kind of looks like. And we know that the early universe is a lot more homogeneous as compared to the late universe. And we know that the degree of inhomogeneity in the early universe from CMB observations is at the level of about 10 to the minus 5. And consequently, we expect something similar for cosmological gravitational wave anisotropies as well. In fact, you can calculate this. And so I've shown you the results assuming adiabatic initial conditions for gravitational waves. And on large scales, these anisotropies are almost pretty much, in fact, identical. But this is not the complete story for such backgrounds, because we know that in addition to this anisotropy, we also have the anisotropy induced due to our motion with respect to the isotropic frame of the background. So in the CMB, the largest anisotropy itself is the kinematic dipole, which is a result of our motion with respect to the isotropic frame of the CMB. And we know from our CMB measurements that this motion has a velocity of about the magnitude of about 10 to the minus 3 times the speed of light, and it is directed in this particular direction in galactic coordinates. Now, if the background is also of early universe origin, if the gravitational wave background is of early universe origin, we expect a similar kinematic dipole whose magnitude is proportional to beta and also proportional to the spectral index of this background. So denoted here as 1 minus Ni. So on top of this monopole, you have this kinematic dipole also for gravitational waves. And there are also smaller contributions starting at order beta square, so quadrupole and so on. But these are very small, so we can safely ignore them. How does the pulsar timing array respond to such a background? So on top of the isotropic part, denoted by the Hellingsdown curve, you also have a dipole correlation function, which depends not only on the angle between the two pulsars, but also on the angle between the pulsars and the dipole velocity. I showed a part of it here in red. It's the dipole response is actually a bit weaker than the monopole, but it can be derived. And using this, we can try to search for it in the current data, as well as try to forecast how future experiments will be able to see or not see such a dipole. But as a side note, I should also mention that there's a tension in cosmology, not the Hubble tension, but a lesser known tension is the dipole tension, in which people have found that there appears to be discrepancies in the magnitude of beta, in the magnitude of this velocity as inferred from large-scale structure or cosmic microwave background experiments. So large-scale structure experiments appear to measure double the velocity, double the magnitude compared to CMB, but the directions are roughly consistent. So in the future, there is potential for gravitational wave observations, not just at PTA scales, but also at interferometers, ground and space-based, to try to also provide their own independent measurements of the dipole.
Is there speculation about why that's happening?
Which one?
The
This
difference?
tension? Too much speculation, probably. I mean, there's so for the large-scale structure, there are many different tracers that you can use to calculate this, and all of them come with their own uncertainties and biases. It's try to combine everything and consistently. I don't think it's easy and probably not going away soon, just like the Hubble tension. Sorry?
This is Jim Peebles?
Peebles has the review on this, but even after this, there's been several papers.
But this is B Peebles, Jim
Yes,
Peebles.
yes. There's another one.
People from Peebles.
Okay, so the first thing we did is to take the current data from the nanograph collaboration, which monitors 67 pulsars for a period of between 3 to 15 years. These pulsars are shown here in elliptic coordinates. And we implement this kinematic dipole correlation function in their code enterprise. And using that, we try to constrain the magnitude of this dipole. So we obtain for the amplitude and spectral index results which are consistent, which are obtained by collaborations. And we are able to put the first upper limits on the dipole magnitude at about at a level of 0.3, 95% credible intervals. Of course, this is quite far away from where we want to be because we want to be at a 10 to the minus 3 level, and we're only at 0.1. So we want to turn to see in the future which kind of experiments will be able to perhaps bring down this upper limit closer to where we want to be. I should also mention that these results assume that the background is of cosmological origin, because if the background itself were astrophysical, I would have to account for all the other anisotropies because of the inherent inhomogeneous distribution of the black holes themselves. So these results only apply for cosmological backgrounds. What comes next for pulsar timing science, gravitational wave science for pulsar timing arrays? So in the next year, it is expected that all these different collaborations will combine their data and release a joint analysis, denoted here as the IPTA DR3, so the International Pulsar Timing Array Data Release 3. And this data set is expected to cut into a significant chunk of the parameter space of the astrophysical anisotropy models. So this would give very strong hints of whether, if the signal is astrophysical, if these anisotropies are close to detection or not. On the other hand, knowing the level required for the kinematic dipole, this is unlikely to be enough. So we try to forecast what might happen with SKA. SKA will be a radio telescope array with telescopes in Australia as well as South Africa, and is expected to launch around 2030s, so maybe 5 to 10 years, I'd say. The good thing is that SKA, the instrument, will have a lot lower noise and is expected to observe a lot more pulsars compared to current experiments. So there is potential to even go further below what current upper limits we have on beta and move closer towards the goal of 10 to the minus 3. So how do we do these forecasts? So at present, given that we don't know much about where the new pulsars will be and what their noise properties will be, we try to develop a simple idealized scenario in which we observe a large number of pulsars, which we distributed uniformly across the sky. And these pulsars have completely identical noise properties, which allows us to, and these simplifying assumptions allow us to carry out the estimates for the forecast completely analytically, but they also represent the most optimistic forecast you could get. A realistic analysis would give you a slightly lower sensitivity, I would expect. So, firstly, the results for a weak signal limit. So assuming that SKA will have noise levels which are greater than the gravitational wave background signal currently seen, it is expected, our results indicate that you would require at least 4,000 pulsars to detect this dipole to even get a 2 sigma detection of this dipole. And naturally, as a consequence of this, the dipole location would also not be constrained too well compared to what constraints you have from the CMB. On the other hand, it is a lot more likely, given that current PTA collaborations already operate in the intermediate signal regime, at least at lower frequencies, and not the weak signal regime, it is more likely the SKA will be in the strong signal regime. It will have much lower noise, in which the observations will be limited just by cosmic variance. So the signal variance itself will prevent us from reaching arbitrary precision on the measurement of these parameters. So with this setup, we showed that even with about 1,000 pulsars, you get the same results that you had in the previous slide. But, and also, I should mention that the error on this dipole magnitude scales as the inverse square root of the number of pulsars. So this is very standard. So forecasts for SK suggest that 1,000 pulsars is not entirely unrealistic. So I would say that this scenario is challenging, but definitely possible with something like SK. So in another paper, we also studied similar forecasts for circular polarization, which is also an interesting observable, which can be produced in early universe models, for instance, involving axions and gauge fields, but also in astrophysical models just by fluctuations of source properties. So this is another interesting observable for which I will ask you to turn to this paper if you want to read more about this. Of course, there's some more work that we're doing with PTAs and related gravitational wave detections, and that is this idea of using stellar astrometry, so measuring the positions of stars, a large number of stars, very precisely to try to detect gravitational waves. So the idea behind this is that gravitational waves, again, gravitational wave backgrounds, produce small correlated deflections across different stars, in the positions of different stars. So in the apparent positions of different stars, if you see some correlated deflections, the correlation again follows a particular pattern, such the same way that in pulsar timing arrays you have the nearly quadrupolar Helling-Stowns. You get something similar here, but it's a bit more complicated because you're dealing with positions, not just scalar functions. And this idea has already been used to constrain low-frequency gravitational waves in this paper as well as several more.
So how many stars do you need to see? Like you need to, in the field of view?
Yes, like millions. So this paper that I'm pointing out already, I think it had a few 100,000 at least. And people have also looked at other data sets with similar numbers. But so at the present...
so this is something you can probably do with what? Gaia data?
Yes, yeah, exactly. So the paper is using Gaia data. So the level, I think, the level of constraint at the moment is about 10 to the minus 4 or 10 to the minus 5 for omega GW, whereas the signal that has been observed by PTAs lies at 10 to the minus 8, 10 to the minus 9 level. So it's still far away, but there is expected to be a lot of improvement because using the full Gaia data, which has not been used yet for the gravitational wave constraints, as well as future experiments as well. So our idea, the thing we are looking at currently, is given that these PTA and astrometric experiments operate in similar frequency ranges, can we cross-correlate across the different data sets to try to improve the constraints that we already have from pulsar timing arrays? So even in the regime where astrometric data alone may not be enough to get any meaningful constraints on gravitational waves, we have some preliminary results which indicate that improvements are definitely possible. But I would say to wait for our paper, which we hope will be out maybe this month or sometime early next month for more details. So to summarize the first part, what I wanted to show to you is that anisotropy could be used to distinguish between supermassive black hole binaries versus cosmological origin of the observed PTA signal, because the detection of percent level anisotropy or larger in the near future would completely rule out the cosmological interpretation of the PTA signal. On the other hand, the much smaller level of kinematic dipole, which is the largest anisotropy for cosmological backgrounds, may be detectable with SK in the future. So that's the first part. If there are any questions, I can answer that. Otherwise, I move to the next part.
So at what confidence level can you tell this?
So which one?
Whether it's cosmological or...
if you see something already in the next data set, you don't even need to mention confidence level because no cosmological model produces anisotropies at the 10 to the minus 2 level.
I see. Okay.
So it's...
Yeah, fantastic.
Yeah. I mean, maybe you can try to really engineer or tweak some model to please that, but that would be really unnatural.
Can I ask a question?
Yes.
To what extent does the sky coverage of the pulsars affect the sensitivity, in general and also for this dipole? Because I guess you're limited sort of along the galactic plane, but I'm not sure how locally.
Yeah.
pulsars? Is it important to have good sky coverage?
Yes. So in general, if you want to reconstruct just the sky map without reference to a dipole, you want to have pulsars distributed as uniformly across the sky as possible, because that helps in sensitivity to different parts of the sky. But also specifically to the dipole, you want more pulsars which are located closer to the dipole directions rather than in lying perpendicular to the dipole because of this factor here. So if the pulsar is perpendicular to the dipole direction, you just have no sensitivity. Does that answer your question?
But yeah, I guess does this help? I guess maybe the answer is yes. Like in terms of the SKA, I don't know how much they have to prioritize which pulsars they look for. So
Yeah,
you're suggesting that there should be some sort of systematic approach where they monitor carefully a particular sample of pulsars so that you have the best sky coverage to do the science that you're interested in.
Yeah, I mean that is true. That is definitely true, because if there's also issues with analyzing very large data sets of pulsars, so prioritizing pulsars according to what your science goals are will be very important, and knowing that for dipole you need to prioritize certain directions is very, very helpful, certainly.
So SKA will have the luxury of being able to pick the pulsars that it wants to.
I cannot say anything about that yet. I'm not a member of SKA, but I expect that next year there's a big SKA meeting in which they will discuss gravitational wave science as well, and things might become clearer after that, both related to number of pulsars that could be used for gravitational science and all of these related issues. Okay, so let's move on to the next part, which is about Bayesian model selection in cosmology. And this is based on work currently in progress with Jan and Nathan at UNSW. So what we're familiar with is one kind of Bayesian inference is to, given a specific cosmological model, we try to get constraints on the model using data. A simple example, or the one you'll be most familiar with, is using CMB data, assuming the lambda CDM model to get constraints on the lambda CDM model parameters. For this, what is typically used are Markov chain Monte Carlo techniques, in which using basically a random walk, you generate a set of independent samples in a way that the density of the samples is proportional to the probability density itself. So the other kind of inference, the one that we're interested in this work, is Bayesian model selection. So this is the idea, given the data, irrespective of model parameters, you try to figure out which model is preferred over the other. For example of this could be, again, from using CMB data, to try to figure out which inflationary potential is favored. For this, you need to calculate what is called the Bayesian evidence ratio. This was done, for instance, in the recent Planck paper as well. They ruled out certain classes of models as well. And the Bayesian evidence ratio itself, using Bayes' theorem, you can write it as proportional to prior probability of a given model times the probability of generating that data conditional on the model. The quantity that we are interested in is what is called the Bayes factor, which is the ratio of these model likelihoods. So the likelihood of producing that data given a model, so the ratio of these two quantities. And the Bayes factor is just the ratio of this. Once you calculate these ratios, you can look up, compare these values to standard tables. So this is called the Jeffrey scale, and using the comparison, you can state whether your model is either favored compared to one, or the decision amongst them is completely inconclusive. So on. To calculate this evidence itself, you have to do a lot of work, because the evidence is defined as an integral of the likelihood times the prior probability over the entire parameter space of your model. The nice thing, though, is that the Bayesian evidence incorporates mathematically the principle of Occam's razor. So it guards against overfitting by penalizing more complicated models with a high number of additional parameters, which are unable to provide significant improvements to the fit to the data. But again, calculating this is quite complicated. And the standard method, cosmology, is to use what is called nested sampling. And this is just a short one slide summary of this complicated algorithm. The idea is to divide your convert your multidimensional parameter space into one-dimensional prior volume space using these nested contours. So each nested contour corresponds to a particular likelihood value. And as you move towards inwards, or as you shrink these nested contours, you move towards likelihood values which are larger and larger. And at the end, you can just calculate the Bayesian evidence simply as the area under this curve. In practice, what people do is use codes like polychord or multinest to calculate this Bayesian evidence. This is certainly quite a complicated task. And we would like to figure out if we can maybe simplify or provide certain improvements in efficiency in certain situations. So these standard methods, MCMC or nested sampling, they work well for the most part, and they're widely used for the same reason. But there is one issue. These methods rely on random sampling, which is both a blessing and a curse. But the issue is that because of random sampling, they're required to evaluate your likelihood at a very large number of points. So for typical examples in cosmology, you would require at least 10,000 evaluations or even more. This can be very problematic if your likelihood function is very costly to evaluate. So if your likelihood takes a lot of time to evaluate, you really don't want to rely on evaluating it thousands of times. So this kind of situation arises when you're looking at high precision settings, for instance, for your cosmological Boltzmann code. You might be testing some deviations from scalar power law spectrum. And for this, you need to really crank up the precision settings on your code, which definitely slows down the evaluation of your cosmology. But also, in general, if you have some likelihood that relies on numerical simulations, you will naturally have a situation where the likelihood takes some time to evaluate. And for these situations, we want to use a technique called Bayesian optimization to speed up or try to evaluate our Bayesian evidence in as few likelihood evaluations as possible. The idea behind the Bayesian optimization algorithm is based on two steps. So the first step is, given a set of training points, you try to guess or interpolate the shape of the likelihood function using these training points. And step two is, using your guess for your likelihood function, you figure out what is the next best point to evaluate your likelihood function at. And this is done using criteria based on some acquisition function. And then you repeat these steps until you're satisfied that your Bayesian optimization algorithm has reached convergence. So for step one, what we rely on is Gaussian process regression. The idea behind this is to treat the function value at each point as essentially a Gaussian random variable with a given mean and covariance function, which can be completely written down in terms of the points at which you've already evaluated the function. So in practice, what this looks like is shown in the following plot. So if you have observations at certain points, your Gaussian process interpolation of your real actual function will pass exactly through the values of the function at those points. But as you move further away from your observations, well, the Gaussian process may or may not, the mean of the Gaussian process may or may not replicate the exact function values, but as you're moving further away, it will show up as an increase in the uncertainty of your knowledge of the function. So an increase in the variance of the Gaussian process at those points. Now, using this Gaussian process regression to model the shape of the function based on some training points, the next step is to decide where to evaluate the next point. And to do this, we make observations based on an acquisition function, the choice of which depends on what your goal is with the Bayesian optimization algorithm. So, for instance, if your goal is to try to find the maximum value of your likelihood, so finding a maximum likelihood, you might turn to the commonly used expected improvement acquisition function, which literally means the expectation value of the improvement over the current best value that has been seen, that has been observed in your training data. So previously, Jan and Ulyss used it to find maximum likelihood, for maximum likelihood analysis of Planck data for feature models, and it worked quite well. And also it's been used in this other paper, again, for cosmological inference, but for the purpose of parameter constraints. Our goal is slightly different, because what we want is not just to learn the maximum value of the function, but rather the overall shape of the function, because we want to do the evidence integral. So we want to know the global shape. For this, we choose an acquisition function, which is suited for this purpose, and which we call the weighted integrated posterior variance, which is simply the mean, which we define as the mean of our Gaussian process times the variance integrated over the parameter space. In practice, we do not need to do the full integral, because we can simply do a Monte Carlo estimate of it by sampling these test points x, because mu itself is a probability distribution, it's a likelihood. So the idea behind this is the idea behind using this acquisition function is to prioritize reducing the global uncertainty of our Gaussian process, while at the same time prioritizing first the regions where we know the likelihood is larger. In practice, here's what it looks like for a simple one-dimensional example. So you start off with an initial set of 2 training points, and your acquisition function, once you optimize it, tells you that you should evaluate it here, because not only is the variance here large, but so is the expected value of the function, so the mean of the function. So the acquisition function landscape itself looks like this, and here we are looking for the minima of this, because the minima represents the lowest uncertainty, or the lowest global uncertainty you would get after sampling your new point. So once you repeat this for a few steps, what you get is you start to learn the function better and better. So the uncertainty goes on decreasing, first at the regions where we know the function is large. And as for the acquisition function itself, its optimization landscape is quite complicated, because it can have multiple local minima. And these spikes here, what they represent are values at which you've already sampled the function. The spikes represent that you don't want to sample the function again here, because if you sample it here, you don't get as much reduction in uncertainty as you would get by sampling it, say, at this point. So once you've trained your Gaussian process using this algorithm, what you can then do is to run your favorite MCMC or nested sampler on the Gaussian process for very cheap. So you don't need to run it on the actual likelihood, but you can run it on the Gaussian process, which acts as a surrogate for the actual likelihood. And running this on the Gaussian process is extremely fast, because evaluating the prediction of the Gaussian process at any given point is much, much faster than evaluating the actual likelihood at that point. Before I turn to more complicated examples, let's discuss some pros and cons of this algorithm. So the good thing is that given that the Bayesian optimization algorithm uses all the previous information that you have about the function that you've collected in all the previous steps, it will naturally converge to the true likelihood shape in far fewer samples compared to the traditional methods. And the other good thing is that it will work for arbitrary shaped likelihoods, which might be multimodal, non-Gaussian, or so on. However, all this doesn't come for free, because each step of the Bayesian optimization algorithm has a much higher computational overhead in terms of memory and CPU time compared to the traditional methods. The other issue is that the Bayesian optimization algorithm, because it's based on Gaussian process, it doesn't scale too well with the number of dimensions. So in practice, we may be limited to say 10 or 15 dimensions, unlike MCMC or nested sampling. But we are also working on that to try to hopefully extend it to even higher dimensions. So here are some more complicated examples in 2 dimensions. So the first one is what is called the banana function, because it looks a bit like a banana. It has this curved degeneracy, which can be sometimes an issue for MCMC samplers. And I compare here the prediction from our Gaussian process or Bayesian optimization fit with the parameter posteriors from nested sampler dynasty. You'll see that the agreement is excellent, and we did this in 60 samples of the algorithm. Whereas if you run the nested sampler directly on this function, you would need, again, thousands of likelihood evaluations. Another, a lot more nasty function is called the Himmelblau function, which is commonly used for testing these optimization algorithms. And again, we showed that with about 120 samples, you can reconstruct this function quite well, and the predictions match very well with those of the nested sampler dynasty.
So why choose this specific type? So is there a bias or is there some peak? Why do you choose this banana and?
I mean, I could also show you examples for like multivariate Gaussians, but those are very simple. So the idea is to take functions which have complicated landscapes, which standard techniques might struggle with.
Yeah, these are standard test functions, like especially nasty examples of functions.
Of course, physically, you probably don't expect to see the Himmelblau in cosmology. Okay, but now we come to an example from cosmology, which shows the working of our algorithm quite well, I think. And in this example, what we're trying to do is to infer lambda CDM parameters from CMB likelihoods. And we show that with about 150 samples, we are able to match the results of an MCMC on the same likelihood very well. And this run, which I did just this week, took about 2 hours on my laptop with about 150 likelihood evaluations. In fact, if you just wanted to get the parameter posteriors, you wouldn't even need to do 150 evaluations. And you could easily get away with 100 or 200. But what we want here is not just the parameter posteriors, but also the evidence. So the Bayesian evidence here. For this, we can get an estimate from a Gaussian process by simply running a nested sampler on the final prediction of the Gaussian process. So using the mean, we get some number. And then we also have the upper and lower limits, which take into account the uncertainty of the Gaussian process itself. So given the fact that these numbers are very close, we know that our algorithm has worked quite well in determining the evidence for this given example. Of course, we also compare it with the results from a standard nested sampler, which finds, and we see excellent agreement in this number and the prediction from the mean of the Gaussian process. The good thing, or the advantage of our method here, is that for the parameter constraints, the MCMC takes about 10,000 or so likelihood evaluations, and the nested sampler a few times more. So in cases where your likelihood is actually very expensive to evaluate, so it takes a lot of time to evaluate, which although is not the case here, but in general, those are the kind of problems where you want to use this Bayesian optimization algorithm. And we show here that it works very well with just a very small number of samples, orders of magnitude lower than the traditional methods. Right, so to summarize this part, what I wanted to show is that Bayesian optimization, which is based on Gaussian process regression plus an active learning acquisition strategy can be used to perform Bayesian inference for cosmology. The algorithm has high efficiency in the sense that it requires far fewer likelihood evaluations compared to traditional methods based on random sampling. And with this method, you can calculate Bayesian evidence for complicated distributions and computationally expensive likelihoods in very few number of samples. Our paper and code, we hope it will be out soon. And the code itself is based on JAX. So if you're familiar with it, you can also use it to leverage hardware acceleration on GPUs and GPUs and so on. So that brings me to the end of my presentation. Thank you for your attention, and I'll be happy to answer any of your questions.
Thank you, Ameek.
Yes, one question. So for the Bayesian optimization, you need that acquisition function as well. So how much more overhead do you have per function evaluation of?
Yeah, so that's something we are at the moment actively testing as well. But the acquisition function can lead to a very large overhead, especially in higher dimensions, because you want to find a point. For instance, if you have a 10-dimensional problem, you want to do a 10-dimensional optimization with some gradient descent method or gradient-free methods. So that is very complicated, and that takes quite a lot of time.
But the function is there simpler to evaluate it, or so you have to do another optimization.
No, so that function you can evaluate very quickly. So that itself is not a problem. Yeah. But the function landscape can be very complicated.
Okay. So you may not find the minimum.
There's no guarantee that you find the global minimum, but I think that's true for whatever kind of optimization algorithm you use.
For the acquisition function, it's not such a big deal. It means instead of the perfect next pick, you merely find a very good next pick. And I mean, if you have 100 or 150 function evaluations altogether, in the end, it probably doesn't matter if you take them slightly out of order.
Actually, from this, even for the simple examples, in some runs, what happens is instead of picking this point, your algorithm might pick this or this, for instance. But given enough iterations, it will then get the next one eventually.
Yeah. Because in the next step, that minimum will have been removed, and chances are a lot higher that you end up in the global minimum in the next iteration.
Thanks.
Do we have any questions online?
Richard was first, I think.
I've got a couple of questions actually. This question was just a technical one. Were you doing that's like doing the Planck likelihood? And there's like a bunch of, it's a while since I've looked at that, but there's a bunch of nuisance parameters, right?
Yes, that's a great question. So in this one, we're using the Planck light likelihood, which has the nuisance parameters marginalized over.
Right.
But we're also testing with the full likelihood, which has all the nuisance parameters. And we have some ideas on how we can deal with that as well. So hopefully we'll have some results soon as well. But it becomes a lot harder and a lot slower because of the increased dimensionality of the likelihood.
Right. I mean, some of these methods deal better with large n than others, right? Maybe this is one we can take offline, but I mean, it was really my postdoc and PhD student, and they both left physics to more lucrative places to apply Bayesian reasoning. But we looked at using basically building an emulator for the likelihood out of the first points, and we got like a 50 times speed up over regular MCMC when we did that.
Yeah.
So it's probably not. Is that a similar kind of ratio to the one that you're seeing? But I can't actually tell you now whether that was with the full likelihood turned on or not. I'd have to go back and check.
Yeah, I see. So you're talking about speed up in terms of time, and not.
Yeah, well, in terms of number of likelihood evaluations. Yeah.
Yeah. I mean, here, for instance, we have 150 compared to say 10,000 or 30,000, 40,000. So again, it's what, a factor of 60, 70, and
Yeah, it sounds comparable. Yeah.
similar. Yeah.
Yeah, happy to. I mean, it's kind of a side quest for me because I'm not working with likelihoods directly.
Yeah.
But I'd be happy to chat about that if there was if I mean it's clear that what you're doing is separate, but I know that yeah, it's sort of something it's something I looked at ages ago actually, or slightly differently, where we were interpolating the WMAP likelihood using a polynomial fit, which is kind of reasonable when you've only got a smaller number of parameters. But this was a much more statistically elegant way of dealing with it.
Okay. Yeah, thanks. We'll be happy to talk more about this.
Yeah, I'll drop you a note.
Yeah. Great. Thanks.
So I had a question about the first half of the talk. You mentioned quite early that supermassive black hole mergers, look right or look consistent.
Yes.
As the origin of this signal.
Yeah.
Now, can you tell me about the role of uncertain parameters of the history in that assessment? Now, the reason I'm asking is the following. I mean, you later talk about the inhomogeneity from supermassive black holes, and that's very intuitive. That it would be inhomogeneous for the reasons you mentioned.
Yeah.
But every time supermassive black holes are mentioned, it's pointed out, look, we don't actually understand how you get to the supermassive black holes of today via merger of black holes in the past.
Yeah.
Therefore, we either don't know the parameters of the intervening history well, or our model of the intervening history is broken, or there's something else going on again. So why doesn't that affect this conclusion? Is it that it's somehow insensitive to the history, or do you not believe the received wisdom that I just spoke, or what's going on?
So all the uncertainties that you mentioned are there, and the papers from the collaborations discuss those in detail.
Yeah.
But unfortunately for you, I don't work specifically on this, so I'm not very well aware of what's going on behind the scenes. So I can't completely answer your question. But if you look at, for instance, maybe I have some extra slides about this. Yes, so I think in one of the papers, what the nanograph collaboration tried to do is, given this, given the observed signal, try to infer some properties of the underlying supermassive black hole distribution. And I think what they found is you only get decent constraints on the black holes, which are the distribution, which are black holes, which are, sorry, closer to us, so low redshifts compared to high redshifts. But all the other issues that you mentioned about how these are formed and whether these can actually merge and what kind of uncertainties there are, I couldn't really tell you more because I don't work on it.
Okay, it feels to me that something non-trivial must be going on, and maybe that the bulk of the signal comes from things that are relatively close to us.
So that is in fact exactly true, because
relatively recent in time, that would make sense.
From this plot itself, you can see, so they've plotted the gravitational wave fraction or the energy density fraction as a function of the redshift, and you can see that most of the signal comes from the very closer redshift black holes compared to the higher redshift ones.
Okay. All right, thank you. Another brief question, if I may. When you introduced the dipole,
yes,
you were speaking of that only, you said, in the context of an early universe origin.
Yes.
is it a stupid question to ask why this doesn't arise also in the context of mergers?
No, not at all. It arises as well for mergers, but the issue is that because it's much smaller, because it's again 10 to the minus 3 in terms of intensity. So in terms of CL, it's 10 to the minus 6. So it will be swamped by this short noise contribution that is intrinsic to the supermassive black hole scenario.
Okay, whereas can you just go to the slide of early universe origin?
Yes.
It can be large in that case. Is that the point?
Whereas in the early universe one, if you look at the intrinsic anisotropy, so the gravitational wave counterpart of the CMB anisotropies,
yep,
they're at 10 to the minus 10. Whereas the dipole is at 10 to the minus 6 in terms of the CL. So it's much larger in this case.
Okay. All right, thank you.
Okay. Do we have any other questions?
One more.
Yeah, sure.
It's just, you may have said this and I may just have missed it, but when you're fitting when people are fitting the cosmological signal and they match it, or the pulsar timing signal, and they meant, like there's a choice between an early universe contribution and a supermassive black hole contribution. Isn't the most likely prior for the early universe model that it would be a superposition of both?
Yeah, you could have both as well. And
but isn't it? If you were kind of isn't it almost true that you kind of expect the supermassive black hole signal to be there at some level? Like, you'd be kind of shocked if you got down to SGWB levels and you hadn't detected it.
Yeah, absolutely. So
and so like in some sense, it's almost like a foreground that has like interesting astrophysical information, just not about the systems that we're looking at. And so if you're, and so like, I think it struck me that a lot of the PTA papers or people fitting that, they seem a lot of the time to be saying, oh, I'm going to fit to to an early universe signal, which will have maybe slightly more convenient spectral shape. But in reality, they should always, you can fit to the present universe signal and it is, it is what it is. And then you think you'd be fitting to like a combination of what you thought the supermassive black hole signal would be combined with some potential early universe signal.
Yeah. That's absolutely right. In fact, this paper from Nanograph, they do both.
Okay. It wasn't, it's just my own ignorance speaking. It's
yeah. So for all these scenarios, they look at just the early universe one, but also the early universe plus the supermassive black hole.
Okay. Yeah.
Of course, at the moment, it's not too constraining, so you can't really say anything about it.
Yeah, obviously.
Okay. Any last question online?